Lucas?
Good
Lucas?
morning.
Yeah, okay.
Yeah.
Wasn't sure you could hear me there for a second. Actually, the audio is super good on your. What do you use for a microphone?
Oh, I just have a headset that I have like for my phone.
Ah, that's the secret, is the headset. I should probably get me one of those. I use a stand-up mic, but I think mine works pretty good. But I'll bet it's not as good as a headset. Yours is noticeably better quality audio.
Yeah.
Oh,
Well, I don't know. I think it's better because the mics and stuff on
hmm
the computers are pretty bad.
Yeah, if they're built in, yeah, that's tougher, I think. So you're not
Yeah.
back in school yet, right? You go back next week?
Yeah, I go back next week on Tuesday.
All right. So let's see if we can cover some more of this material here. Pretty straightforward up till we get stuff like this one. We covered this square root of x last week. And remember what we had to do here? We had to write this one as y equals the square root of negative x minus 6.
Yeah.
And then this becomes f of negative x minus 6. And you can always check to see that you've done it right. In other words, let's say we make the most common mistake that everybody's going to make here. They're going to write this thing as minus x plus 6. Okay?
Mm-hmm.
And now, if we were to write that as f of minus x plus 6, we don't get the right 0 point. In other words, x at 6, if you look up under the original function, x at 6 is where y is going to be equal to 0. But
Yeah.
if I use that, it's x of minus 6 is where y is going to be equal to 0. So you got to be a little careful when the x has a negative and you're subtracting. This is a little more complicated still because you have to factor out the 2. So this one here would end up being written f of 2 times the quantity x minus 3.
Yeah.
All right, let's go to natural log. Here, hold on a moment. Let's skip to the difficult ones. I'm sure you know A, you know B, you know C, you know D, you know E. What's that one look like? F.
Um,
Here, let me draw
what
the
what's
natural
the
log.
parent function?
The
I
parent
can't remember
function
what the
is
parent
natural
function
log,
is.
which looks like that.
Okay. So it would just be like it would be it just doesn't cross the x-axis
A little
and like that.
tricky. Actually, the answer is it is both a reflection over the y-axis and the original function. In other words, the fact that I put absolute values around the x opens up my domain. Now I can have positive and negative values for x, because even a negative value for x is going to turn into the log of that positive number.
Yeah.
Okay? So it's basically a combination of that and that. This side being that, this side being that. And it's
Mm-hmm.
both. And notice that there's still a vertical asymptote at 0, because x can still not be 0. You still cannot take the natural log, or any log for that matter, of 0. Remember, the domain on log is more restrictive than square root.
Yeah.
Y equals square root of x. The domain is all x greater than or equal to 0. Y equal log of x. The domain is only x greater than 0, not greater than or equal to. Okay, this one's fairly straightforward. Tell me what this one is.
That's a vertical stretch.
No, the 2 is in front of the x, not the function.
Oh, okay. So it's a horizontal.
Vertical when it's in front of the function. In
It's
other
a
words,
horizontal.
yeah, this is going to end up being f of 2x. The difference being that would be that's a vertical stretch. That's a horizontal squeeze. Shrink.
Mm-hmm.
Because it's greater than 1.
Yeah.
And of course, the minus 4 is relatively straightforward. It's f of 2x minus 4. So that's the vertical shift down. Okay.
Yeah.
And in this one, I need the next page. The parent function is 1 over x. And so what is a? In other words, let me write the parent function, and I'm going to use f of x notation here because I think it's a lot more valuable than y notation. Y notation does not allow you to go in and define the translation in the f part of the notation. So what is 1 over x minus 2?
That's
It's the same as what? Tell me what that is in terms of f.
That's the same as 1/2 x. No.
No. Remember this. You cannot separate this into two fractions. That is not the same as 1 over x minus 1/2.
Yeah.
The only time you can separate it is you have a single entity in the denominator and multiple entities in the top, then you can separate it out into separate functions.
Yeah.
This is what? F of x minus 2, right?
Yeah.
In other words, if this is f of x minus 2, I would merely replace the x with the x minus 2, and I would end up with that. And what is this? In other words, the secret in all of these is figure out how to write it in f notation. And once you've done that, then this tells you immediately that it is what?
That it's a horizontal shift.
Which way?
To the right.
Okay, good. And that's the same thing, only to the left. What's this? What's negative 1 over x?
That's a flip. It's like reflected over the x-axis.
Yeah, and you shouldn't really have to think that hard on that.
Yeah.
In other words, if I said y equals 3, is that horizontal line? Well, if I said y equals negative 3, it means every point that's there has to be the same distance from the x-axis, but on the other side. So the leading negative sign of any function is always a flip over the x-axis. What is this one? In other words, we'll say y equals 2 over 5 minus x. First of all, how are we going to write that as that notation?
That would be it wouldn't be 5 minus x, would it?
No. Well, it would, but that doesn't help you figuring out what's going on. In other words, yeah, I could write this as f of, well, first of all, where's the 2 go? Go inside the parentheses or outside?
Outside.
Yeah, in front. In other words, this is the same as 1 over 5 minus x times 2.
Yeah.
Okay. Now the question is, what goes on the inside? How do I state this inside so that I'll know what's the horizontal translation, and yet I can't write it like 5 minus x? That doesn't tell me.
It's, would it be negative x plus 5?
Minus 5. Again, we have to do that same adjustment.
Okay.
Okay. Notice how I would translate that relative to that. I would be 2 times, and then wherever I have x, I'm going to substitute that and put a negative sign in it. So it's 1 over, there's a negative sign there, x minus 5, and now that is indeed what I'm looking at.
Yeah.
That's the same thing. 1 over negative the quantity x minus 5, all times 2 is the same as that. So I've got it right, and now all I have to do is figure out what this means. Well, the leading negative means a reflection over what? When it's inside the parentheses.
It means that it's flipped over the x-axis.
No, the leading negative in front of the function means flipped over the x-axis.
Oh, yeah, that's the y-axis.
It's got to be the other one. There's only two reflections. You can either go over the x or the y. And this is the other one.
Yeah.
And then this part here tells you have a translation to the right of 5 units.
Mm-hmm.
Well, let's see if we got it right. We can tell pretty easily. Here's the function 1 over x. Okay. Well, I can look at this and tell that x equal 5 is where my new vertical asymptote has to be.
Mm-hmm.
Okay. For me to move this vertical asymptote that's currently the y-axis, I know it has to be at 5. Everything has to go this direction, first of all.
Yeah.
And then, oops, hold on a second. I made a mistake. You flip first and then move everything. So the first thing I do is flip about the y-axis. Notice that with this particular function, a flip over the x-axis results in the same thing as a flip over the y-axis. But that's kind of unique to certain functions. Not obviously all functions aren't like that, but this is.
Yeah.
Notice that if I flip over the x, I have my blue lines, but if I flip over the y, I also have my blue lines.
Mm-hmm.
So we flip first, and then we move everything 5 to the right. So now my new function, there's the new asymptote. And there's my graph. So when you're doing these difficult ones, after you've done it, always kind of verify that the key points are in the right spot. The key point being, where is the vertical asymptote? Greatest integer function is a bit tricky. For some reason, the first time I did these greatest integer functions, I really had difficulty with them. Let's not spend a ton of time on these because I want to get to some of these lower ones down here, especially these inequality quadratics. It's not obvious how to solve those at all. But the greatest integer function, that's just clearly what?
Jesus, I like don't remember any of that.
Okay, what you have to remember is what these mean. Here's what you have to remember. What's that?
That's a. I wrote those down.
It's a vertical,
That's a.
vertical stretch.
Yeah.
Okay. What's that? When you take the C and put it in the parentheses next to the X?
Horizontal stretch.
Or shrink, depending on whether C is, both of them are, depending on whether C is greater than or equal to 1.
Mm-hmm.
What is this? Whoops.
That's a horizontal shift.
To which way?
To the right.
If C is positive, okay. And this one is really the easiest one of all.
Horizontal shift.
No, vertical shift.
Or vertical, yeah.
In other words, it's the opposite of this.
Mm-hmm.
Notice that every time the C is inside the parentheses, it's horizontal. That's horizontal. That's horizontal. When the C is outside the parentheses, it's vertical. That's vertical. That's vertical.
Yeah.
Okay, and the only other two are where you have a negative sign. If the negative sign is in front, reflection over what?
That's the reflection over the x-axis.
And if the vertical sign is inside, if the negative sign is inside,
it's a reflection over the y-axis.
All right, so those are your basics that you have to memorize. And this is really the page you should memorize.
Yeah.
Because all of these problems are exactly the same. It's which one of these 6 are we looking at? When we look at a transformed function, what is it? Well, let's look at this middle one. In other words, that top one is clearly this, f of x plus c.
Mm-hmm.
Well, the middle one is which one?
That's a horizontal
stretch.
Horizontal stretcher.
Which one?
Stretch?
Stretch or shrink?
I think it's stretch.
The other way around.
It's shrink.
This is a stretch if c is greater than 1. It's a shrink if c is between 0 and 1.
Okay.
This is the opposite.
Yeah.
If c is greater than 1, it's a shrink. If c is less than 1, it's a stretch. So in this case, we have a shrink. Remember what this function looks like. So what would a shrink look like?
Would it just make each one of those sections shorter?
Yeah, let me draw it in blue. And I'll draw it right above the other one.
Yeah.
Okay? So that looks like we've horizontally shrunk it. That looks right, but let's check some points just to make sure that it is. This is at 1/3. This is at 2/3. And this is at 1.
Yeah.
So if we take the point 1/2, does our blue graph reflect that properly?
Mm-hmm.
It does, because 1/2, which is between 1/3 and 2/3, should give us a value of 1. Oh, if I substitute 1/2 for x, I get the greatest integer of 3/2, which is 1. So it puts it on the right line. And then
Yeah.
if x is 1/3 exactly, then 3x is the greatest integer of 1, which is 1, so that's perfect. So this graph does reflect properly. And finally, let's look at the bottom one. It's another way of writing that bottom one, even as y notation.
Negative quantity x minus 3.
What's the sign in front of 3?
Oh, plus 3.
Okay. So that's the same. In other words, I can switch them. Associative property holds.
Mm-hmm.
So what is this?
That's a vertical shift.
Okay, but
Up.
always do your reflections first.
Oh, yeah. So that's a reflection over the y x-axis.
The x-axis, the negative sign.
Yeah.
The negative sign is not inside the greatest integer function. It's outside.
Yeah. And then it'd be a vertical shift up 3.
Yeah. So I would take this exact graph, and when I reflect it, I get something like this. And now I take that graph and move the whole thing up 3.
Mm-hmm.
So the first line becomes that, the next line becomes this, and the next line becomes that.
Mm-hmm.
And then you could plug in, always as a last check, especially on these tricky ones, always as a last check, at least test 1 point to see if you've got it right. Okay, what point should we test? Let's check a point out here in the Netherland here, where x would be 2.5. Should y be 1 when x is 2.5?
Yes.
Yeah, if I plug in 2.5, the greatest integer of 2.5 is 2. So now we have minus 2 plus 3, 1. We're right there where we should be.
Mm-hmm.
Usually 1 point will verify for you that you've done it correctly. You don't need more than 1. Because usually if you've made a mistake, it's in the reflecting over the wrong axis or something that will show up when you try 1 point.
Yeah.
All right. How do they compare for values of x greater than 1? This gets bigger. This gets bigger. Gets bigger. What happens to this function for values x greater than 1?
It gets smaller.
Yeah, take 8 to the 2/3. First of all, what does 2/3 mean?
It's the squared, no. Yeah, 8 squared, then the cube root.
Right, but if you're actually doing the math, it always makes sense to do the root first.
Yeah,
Why? Because if I have to do 8 squared, which is 64, and then take the cube root of 64, I might need my calculator. But if I do the root first, the cube root of 8 is 2, and then 2 squared is 4, so I never deal with a number greater than 8.
yeah, that was just like how I was
All right.
setting it up in my head. I'm sure I would do it the way you did.
Yeah. The biggest thing is to know the meaning of that.
Yeah,
The
that was
denominator
what
is
I was
the root, the numerator is the...
that was what I was trying to like figure out in my head.
Okay. All right, how are we going to do 10? Whoops. Yeah, we'll do 10 and then I'll let you go.
Okay. I don't know.
How would we do 10? Do you know how to manually do it?
No, I don't.
I don't either.
I don't remember it.
There's no technique. You don't remember because you haven't been taught it. In other words, when you have to find the zeros of either cubics or quartics, and they get harder the higher up you go.
Yeah.
But there's no such thing as a quadratic formula for a cubic.
Mm-hmm.
The only way to find these zeros for this function right here, well, I don't mean the only way. The only way for high school students or college students, they may teach this in graduate math on how the technique you would find the roots for this.
Yeah.
You've always got the rational factor theorem, which you could use to find one root and then maybe another root. And then if you can whittle it down to a quadratic, you can always use the quadratic formula to find the last two roots. But
Yeah.
that's essentially the technique when you have things greater than quadratics, is you try to find one root at a time, whittle it down. Once you get a quadratic, then it's easy.
Mm-hmm.
But for us to do this, we need to graph it and find the zeros.
Mm-hmm.
So you need to be able to do that on your calculator.
Mm-hmm.
You can do
Yeah,
that.
I know how to do that.
Okay, cool. Same thing for this.
Mm-hmm.
This is particularly tough to do because it's a mixture of polynomials and transcendental functions.
Mm-hmm.
In other words, I've got a sine of 2x and a 4x. I don't have the algebra to solve that. If I told you x was equal to the sine of x, I have no idea how to solve that other than graphing it. And in fact, if I was trying to solve that, I would just let y equal x and y sub 1 and y sub 2 equal sine x, and wherever they cross, that's the solution.
Okay.
Okay? All right, so Thursday we'll pick up and finish up the rest of these.
All right, cool.
All right, Lucas, have a good couple days here. Talk to you.
You too.